In our final example from section 9.3 here, example 3 part B, we're going to sort of take a different look at the summation expression that we saw in part A. So hopefully you've already had a chance to see example 3A, and if so, this will probably make a lot more sense. As you recall from example 3A, part A, we decided that this summation expression would best be analyzed by using the integral test. And we went through the whole process of finding out that the integral test can be applied because this function would be positive, it would be continuous, and it would be decreasing for values of n that are greater than 2. And in the process of doing the integration, we ended up having to use a not so tricky U substitution. So let's just kind of recap that setup if we could here. We would go ahead and call our function once again f of x equaling 1 over x ln of x to the p, and we would actually take the integral as from 2 to infinity, which is better set up by approaching it from a limit standpoint and integrating from 2 to b. Now, as you can see, the directions are a little different with this example. We want to figure out the values of p for which this series will converge. So apparently there are some possible exponents of p that will make this series converge and not diverge like it did in example A when the p-value was equal to 1. Now, I am not going to go into all the detail of the integration as I did with part A, but if you can recall, the u substitution would take place. Your u would be the natural log of x. You would have a 1 over u form, and essentially what this would boil down to is that we would be dealing with a limit as b approaches infinity of the integration of what would be a 1 over u to the p. Now you got to think of this as being your setup for your integration after the substitutions are made and so forth. And if this even helps, you could think of this as being u to the negative p power, and you'll find out that that integrates very, very easily. You would take your u expression, which is natural log of x, and raise it up a power higher than negative p, which is negative p plus 1, and then of course you would put the negative p plus 1 into the denominator, and then you've got your boundaries from 2 to b. Now, to finish this, you're going to have to sort of take a little bit more of an intuitive approach than more of a calculation type of approach. And you want to be very cognizant of the fact that this guy up here, this ln of x in the numerator, is going to, as b gets very, very, very large, is going to go somewhere, for lack of a better word. And by go somewhere, I'm kind of referring here to this exponent and the fact that, you know, the negative in front of the p does suggest that the quantity negative p plus 1 could be negative. Now, why would we want negative p plus 1 to be negative? Well, let's write that statement here. We want negative p plus 1 to be negative, or less than 0. Well, if this exponent were indeed negative, as you know, that would cause the entire expression to jump down to the denominator and then allow the denominator to grow big, which allows our sequence itself to grow very, very small. And when we add up several of these terms for our series, we would then have the possibility to then converge. And that's exactly what's going to happen here. As long as the natural log of x will stay in the numerator, we are going to be in a divergent situation. So it's simply a matter of saying that exponent must be negative once again. And if we just simply subtract 1 to the right, multiply both sides by a negative, and don't forget to flip the sign, it'll take a p-value that's larger than 1 for this particular series to converge.